other people may be joining anytime. So I can't recognize all names. I hope some of the new students, new postdocs join us because this is really important for them. Important for everyone, but particularly important for them. Good morning, welcome. So today starts our faculty seminar as in the past for the old people. We all know every first Friday of the fall semester, we have a faculty seminar for the whole day. We invite 6 to 8 speakers to give talks of their research, of their labs. This is beyond our weekly seminar series. The purpose is to mostly to have in-reach and also have outreach. So this is important for new students, new postdocs, new staff to get familiar with our faculty to facilitate interaction. This is actually the first time we have the seminar in a virtual environment. I don't know how it goes. Hopefully this is the last time we do this. Oh, we do the virtual seminar, not the last time we do faculty seminar. Okay. Today we have 8 speakers from all 4 major disciplines of marine science. They cover a variety of topics, okay, from benthic mapping to water column chemistry to Southern Ocean, all kinds of topics. I hope this is just a start, not a stop, not an end of the interaction. The seminars will be recorded thanks to Renate, who set up this Teams meeting, and she's the owner of the meeting. I'm not. I'm just like you. I'm a guest. Okay. So in case my internet goes out and she will continue, she will let everybody in and she will try to answer questions on connection. Okay. So the seminars will be recorded, and if people miss this, they can watch online afterwards. So our first, before I, okay. So let me ask everyone to please mute yourself if you don't talk. So just in case we want to avoid echo, noise, and maybe the video will use a lot of bandpass. So if you don't talk, perhaps you can turn off your video also. Okay. So let me share my screen, and I have a schedule here. I think you can see my screen now, I believe. This flyer has been circulated for a few days. As in the past, we have 2 speakers giving the talk in a row, then have a coffee break, but unlike in the past, we don't have coffee now, so you'll be on your own. Then we have a lunch break. This lunch break is a little longer than the past because Maya has the professional development class. Then in the afternoon, we have 4 other talks separated by a 10-minute break. Then at 5, I believe this is our faculty get-together, happy hour time. So we continue at 5. So our first talk would be given by Steve Morawski and Chet Lemke. And Steve is a biological oceanographer focused on fisheries. And Chet Lemke is a physical oceanographer who leads our glider team. So they will talk about mapping of West Florida and Gulf of Mexico. Steve, it's yours.
Okay, thank you, Xuanmin. Let's see if I can get this right.
Share my screen.
Can you all see that screen?
Yes.
Yes.
Great. So welcome to everybody, and particularly welcome to the new students and Dean Fraser. We're very happy to contribute to this seminar series. Chad and I are the faculty sponsors for what is a very large project that we've been working on for the past 5 years related to bathymetric and habitat mapping on the West Florida shelf. And in particular, this is not our work, it's the work of a relatively large team of, it actually expanded to about 14 people at its maximum. We've lost a couple to the US Navy who are mapping something somewhere. I'm not sure exactly what they're doing. And Gerardo Torre Farmer is now a faculty person at Eckerd College. So what we want to do is to talk a little bit about bathymetric and habitat mapping, some of the work that's gone on in the past, our current work and work that's ongoing now, and maybe a little bit about the future. So in terms of an overview, we really want to talk about 4 things. Number one, the mapping imperative. Why is it important for us to do mapping, particularly from a research point of view? That is, maps are important for a variety of societal needs, but how does it relate to research, both in geological aspects and ecology? Secondly, Steve? I'd like to turn back the past a little bit and talk about some of the mapping efforts that have gone on at CMS. There's been intensive mapping going on since the 1990s, and some of these studies really set the base for where we are now. Thirdly, I'd like to talk about some current projects, in particular the large project that we have funded through the National Fish and Wildlife Foundation, and then some of our technologies and capabilities. And last, a little bit on what we hope is a substantial future in mapping as we go forward.
Steve, there's been a request to turn your slideshow into a full slideshow. Is there a way you can do that?
I'm sure there is.
Oh yeah, sorry, that was me. So what I see is the main slide on half the screen and then like the next slide on the other half.
Oh, okay. Well, you're seeing stuff before I...
This happens when you use a double screen and your slideshow is on the secondary screen, then it shows both. So if you switch screen or turn off your double screen option, then it works.
Nice.
But this is not on slideshow.
How does that work? How does that look?
You can.
It looks better now on slideshow. Little icon on the bottom.
Let's see.
There you go. Getting close.
To the right.
There.
Yeah.
That doesn't seem to want to do it either.
Click. Or if you enlarge your screen to full screen, that should also work.
Do you have a second monitor plugged in?
I do indeed.
If you unplug that, then that might do it.
Yes, that's usually the problem. It's a double monitor problem.
All right. Let me try this again. How was that?
It's the same.
Still doing it.
If you
Click on display settings.
If you exit the screen and then you uncheck this part that says use presenter mode, so just exit out of your presentation, like press escape or something. And slideshow, yeah.
There you go.
Or there you go. There you go. Perfect. Boom.
All right. I want my time back.
You got it.
All right.
So Basically went through this overview in terms of why we need to do mapping. And certainly one thing we want to concentrate on is the imperative for mapping. In terms of why must we map the oceans, sort of everybody knows the exploration side of this, that, the dark side of the moon and Mars are known better than the oceans. That's sort of a given. But in terms of the importance to society, there are a number of things that our mapping programs are really focusing in on, and that includes identification and protection of what we would call essential habitats. And those essential habitats are dictated by many of the laws that we have in terms of habitat protection for fisheries and endangered species. Obviously, knowing where the high producing habitats are in terms of managed species is important because it helps us improve our monitoring of them. And that is in places like West Florida Shelf. It's a large sand area with intermittent hard bottom, and those hard bottoms are the places where most of the species reside. And I'll talk about that in a minute. But there are other things in terms of finding beach sand for beach nourishment and the emerging field of ocean mining for rare minerals, and then of course things like safe navigation, piloting, and response to coastal disasters like the current hurricane. So there are a number of mapping initiatives that are ongoing globally from the international, national, and the regional perspectives. The international one is one called Seabed 2030, which is a consortium of the Nippon Foundation and JEBCO, which is kind of in charge of marine charting for the world. And their stretch goal is to actually map all of the world's oceans by 2030, 10 years from now. And about 25% of the world's oceans have been mapped, so that's a real stretch goal. The White House issued a memorandum in November 2019 dictating that we should have a priority of mapping the US EEZ, and in particular focus on the Alaskan nearshore. Not so many people up there. Certainly we would contend that maybe Florida might be a better target. On that regard, some of the states have stepped out on this. California had a seafloor mapping program that they initiated in 2017, and they're pretty much done with it now. You can see California has a long coastline, but it's relatively narrow with a 3-mile jurisdiction. Florida's territorial sea is much bigger, primarily because in the Gulf of Mexico, the territorial sea goes out to 9 nautical miles. Within Florida, there's something called the Florida Coastal Mapping Program that Cheryl Hapke, who's on the research faculty here, is spearheading. And then even the Florida Recovery Act Centers of Excellence program is interested in mapping as well. So there's lots of different initiatives ongoing. So other countries have done this as well. In fact, the country of Ireland has had a goal of mapping their entire EEZ, which they have done. You can see that the EEZ is much bigger than the country itself. They did this because they had a priority. They built 2 ships to do it, and they spent about 10 years doing the mapping. So it's a much more difficult issue for the United States to do this because our EEZ is the second largest in the world, and the mass of the EEZ is about 1.5 times the size of the continental United States. So it's a big deal. So in terms of a little closer to home, what are the mapping priorities? And it's really interesting because eastern Gulf of Mexico shelf is one of the most poorly mapped areas in the entire lower 48. So if you look at this map, this is a compilation by NOAA's National Coastal Environmental Information Center, and you can see that there's a real dearth of multi-beam mapping data, particularly for the continental shelf. And it's interesting because if you look in the deeper water, BOEM, which is the Bureau of Ocean Energy Management, was able to actually get information from the oil industry's seismic surveys and make a pretty comprehensive map of the deep water. But it's this shallow water that becomes a problem. And one of the issues here, of course, is that we have an oil industry in the Gulf of Mexico that's moving ever farther east. And in fact, if you look at the graph on the left-hand side, you can see that the new oil leases that are coming on, particularly in this region down here, are coming along the Florida escarpment. And in that region, there's a current moratorium on new oil leases that extends out to about 125 nautical miles. That moratorium is up in 2022. There's a lot of pressure to move the inshore boundary of this, but to what end? I mean, if we don't know what's there, how do we know that we can protect it from the impacts of oil drilling? So with that being said, there's a long history of mapping research that's been done at the College of Marine Science. And I wanted to point out this particular study by Al Hine, Dave Nahr, Stan Locker, and their students. And this was the first comprehensive map of an area called the Florida Middle Grounds. And you're looking at the bathymetric map that they detailed. It was a really important study. And this, based on this study, this was designated as a habitat area of particular concern, and basically a marine protected area for some activities. But of course, they were also interested in the marine geology that went on in the Florida Middle Grounds. And so you can see that they've interpreted a lot of the geological processes that gave rise to the configuration you see here. 10,000 years ago, this was the coast of Florida. And so you can interpret this in terms of the types of geological processes that occur at the coast. In terms of another study, let me get back here. This is a study by Al Hine, Stan Locker, and others in a place called the Sticky Grounds, which is due west of Tampa. And you can see that there's these really high carbonate formations that are about 130 meters deep. And so they did a mapping project, and here's the results of their multi-beam mapping. You can see that these are extensive areas that occur in this particular region. And they went one step further and actually used an ROV to actually identify what was going on here. It's certainly a very complex area geologically and a biological hotspot. So these are just two of the studies that precede the work that we're doing. So I wanted to talk a little bit about the objectives that we had with our mapping program that has been funded by NIFWF. The goals of our program were to provide about 2,400 square kilometers of new high-resolution bathymetry, to assess the relative density and the absolute abundance of both fishes and sea turtles in those areas, to develop methods to reprocess the existing multi-beam data in other areas so that we could go from bathymetric maps to habitat maps, which are really important, to provide information to the Gulf of Mexico Fishery Management Council and the NIMS to consider additional marine protected areas and habitat areas of particular concern, to work on new technologies and methods, and to identify promising areas for future sampling. So there's a lot of objectives embedded in that project. So one of the things we did initially was, number one, the gray areas were areas that were previously mapped. But in terms of trying to identify areas where we would do this 2,400 square kilometers, one of the data sets we had available from a different project that we had ongoing was the results from vessel monitoring program information from reef fishermen, basically satellite tracking data. So after filtering out the steaming vectors that all the ships had, you can see that there's a large hotspot of fishing effort for reef fish right between some of the areas that had previously been mapped. And so this was a target location for some of our work. And so the areas that we've been able to map in this program are defined in the red, and they include a place called the Elbow, which we'll talk about in a minute, and then this large area that's contiguous with the other two. So in terms of our project, it's based on three important technologies. Multi-beam echo sounder technologies, both pole-mounted and hull-mounted in the two ships that we have, the Weatherbird and also the Hogarth, and then towed video, and this is based on a technology that we developed earlier with a grant from NIMS to basically do towed video and count fish, and certainly the water column sonar Simrad EK60. So the first order of all these things was compile a variety of different data sets. With bathymetry, you get the water depth, but you also get this backscatter information, which is the hardness of the bottom. We're able to take the environmental sensor data and the habitat information from videos, and then actually analyze the video transects for fish and turtle abundance, and then biomass information from also the echo sounders. So that allowed us to do these interrelational analyses. So for example, the fish and habitat associations, the benthic habitat characteristics that go along with the bathymetry, and ultimately these products, which include species habitat maps and stratified population estimates. So just in terms of what we're able to accomplish in this project, we've mapped about 2,350 square kilometers. This involved 172 days at sea, probably about $1.5 million for in terms of ship time. We had about 2,500 kilometers of video, times 6, which is the number of cameras on this system. So tremendous amount of video, and so quite a bit of stuff that was accomplished during this project. So this is one of the contiguous areas. This area south of the middle grounds is new areas that have been mapped. And you can see that in terms of the geological features, they're quite contiguous with what was mapped previously. Now I'm going to try to show this video. I'm not sure it's going to work in terms of people's bandwidth, but it starts way down here at the end, which is basically the end of a barrier island, probably about 12,000 years ago. And so you can see that, hopefully you can see some of the snapshots here. It's a really rich geology across here, and there are quite a few ledges and areas of extreme slope. And it certainly maps together directly with what we learned about the Florida Middle Grounds from previous research. So, in terms of the bathymetry and the backscatter data, we also, as I said before, used the towed video system called, the acronym is Seabed, has 6 cameras. And what we wanted to try to do is marry the multi-beam sonar data with the video data. And it's not a trivial problem to actually figure out where a towed video is relative to the ship. GPS doesn't work underwater. And so a lot of the calculations we have are trying to calculate the layback, that is distance from the ship to the towed video system. And there's some geometry that goes into doing that. And so by marrying up the position of the video imagery with the multi-beam, we can interpret what the geological features are that the multi-beam is seeing, and then interpret the biology as well. So I'm going to show a video from the towed camera system. This is an area called the elbow. The video will go across the hard bottom part of the elbow. I'll try to stop it and show you some of the biology of animals here. You can see, I hope you can see this, there's a hogfish here, a bunch of gray snapper and some others. As we approach the top of it, you can see these are the hard bottom carbonate reefs right here. And this is where the majority of the fish are. And then once you get over the other side of this thing, you can see back in the sand, there's hardly any biology at all. So one of the problems that we have in terms of extrapolating the multi-beam data into the habitats and counting the fish is that even with a video camera that may be sweeping 10 meters on a side, with video transects, you can only do a very small fraction of the area. So for example, these are video transects in the location of the elbow region, and we were able to put eyeballs on about 1% of this habitat. So the issue becomes extrapolating from this 1% to what all the other habitats actually are. So this is a result of work that one of my students, Alex Illich, has done in terms of using a regression model that takes the habitat characteristics from the 1%, which include both the bathymetry and the backscatter, making what we call terrain attributes. That is, things like the bathymetry, the slope, et cetera, and then also texture metrics. And that is from the backscatter data, which is the hardness. There are these grayscale metrics that you can develop. And so by using a regression model that basically trains the data set from what we actually put eyeballs on, and these other metrics that are available for the entire multi-beam series, then we can basically try to classify the habitat. And so for 3 different areas, the elbow, Florida Middle Grounds, and the southwest part, the new part, we're able to look at the variables that are most deterministic in terms of classifying these habitats. And so, for example, in the Florida Middle Grounds, it's the bathymetry itself, as well as the grayscale mean, whereas in a place like the elbow, it's the slope and the standard deviation of the slope, that is how much rugosity there is, that are determinant. So this is a really important development. So if we look at the elbow, you can see that the vast majority of this would be classified as rock habitat, as sand habitat, well over 80 kilometers of it, and only about 3.5 kilometers would be classified as rock, right? So the interesting thing is when we take the video data and assess the density of animals on the various habitats, you can see that the rock habitat has very high densities of certainly all fish, but most of the species that we're interested in, other species like sand tilefish naturally are a little bit more abundant over the sand. And so one thing we can do is, now that we know that the total area is and the relative densities, the absolute densities on each of the habitats, you can expand these by just multiplying through to get, in this case, the abundance of all the fishes in that region, as well the abundance on the different habitats. So for example, because the sand habitat is so big, even though the density is low, you expand it by the large number, and you get, just about 50% or a little bit more than 50% of the total fishes are in 4% of the habitat. And this is differential depending on which species you're looking at. So this is really important because this allows us to use habitat stratified abundance measures and absolute population densities, which is really important from a fishery management point of view. So using this supervised classification methodology, Alex was able to reprocess all the multi-beam data so that now we have these same kinds of classifications of rock versus sand for all of the areas that have been multi-beam. So this is a really important development. One of the other aspects of this is that we've been able to also look at sea turtles. And over the course of the study, we've seen nearly 80 sea turtles on the bottom. The vast majority of which are actually on this single pipeline that exists from Tampa Bay up to Mobile Bay, and that pipeline is called the Gulf Stream Pipeline. After you basically do the density calculations for the turtles, it turns out that turtles are 37 times more dense along the pipeline than they are on natural habitats, and so that begs the question of whether or not the pipeline should be considered a habitat area of particular concern for turtles. That's a joke. So other things that we've been able to see are cultural resources like shipwrecks. This is one that's very well known. This one is somewhat unknown. I think some divers have been on it, but it's probably a 19th century vessel. You can see an image that we were able to shoot. These are probably hardened concrete that particular vessel was carrying. We also see other cultural resources like anchors, and in this case, a stray torpedo that's actually in the Florida Middle Grounds area. We'll talk about that if you want. One of the newer parts of this technology that we're trying to develop is the ability to, sorry about that, the ability to auto-classify as opposed to classifying all this imagery by hand. And so one of the things that we've been working on with SRI International is an algorithm where we can actually separate the fish and some of the habitat attributes from things that are going on. And so you can see that in general, there's mostly correct classifications, a few false positives and a few false negatives. This will revolutionize this whole aspect of trying to, in this case, count the fish on 2,500 kilometers of video. And one of the points we want to make that's pretty important is that we need to understand the geological setting that we're dealing with. And so this is a study that Stan Locker did where we used a low power air gun called a bubble gun to look at the seismic profiles along some of these areas, like, for example, the elbow. And this allows us to interpret the geology. So, for example, at the peak that I showed you before, this is all lithified sand into rock. And it's really interesting because it's only about 10 or maybe 12,000 years old. And so even within that short period of time, the sand has been able to lithify into rocks. And the reason this is important because it allows us to do a little bit more prospecting on perhaps other places to actually sample. And so, for example, if we can start extrapolating some of the other areas that aren't mapped, there are some obvious targets for other programs to actually go in and do additional mapping. So, for example, if you look at some of the low resolution bathymetry, you see these, I call them cul-de-sacs, of which the elbow is one, and these are likely targets to be the exact same things that we've been able to map before. But there are other contiguous shorelines and banks and other pinnacles and mounds to be mapped out there. So in terms of the future, I want to just have a couple of slides here and finish. First of all, we owe a final report for this large program to our funders, but also we have an appointment to talk to the Gulf of Mexico Fishery Management Council Scientific and Statistical Committee to talk about the importance of this. We are part of a large experiment called the Great Red Snapper Count, which is trying to do an absolute count of red snapper in the Gulf of Mexico. Our particular parts of that project were counting red snapper on pipelines, which we are very good at, both in the east, but especially in the west. There's about 67,000 kilometers of oil and gas pipeline. We have a project that we, because of the COVID, we haven't been able to get out on yet. It's called the Big Bend Demonstration Project for Noaa, which we will do. We certainly want to be part of the Florida Ocean and Coastal Mapping Initiative. I'm going to talk a little bit in just a second about the proposed Center for Ocean Mapping and Integrative Technologies. And then there's tons of other opportunities in research here and a lot of data from which different student projects can be developed. The next in the queue, as I said before, is the Big Bend Mapping Demonstration Project. And in this project, we're going to try to extend from the offshore work that we're doing into the inshore. Now, certainly we can't mow the lawn in terms of the entirety of these wedges, but what we're going to do is try to do some prospecting to see, particularly this area where the bathymetry converges, and then this area here where it's highly rugose. These are likely areas of other important habitats, and so hopefully we're going to get 3 back-to-back cruises on Hogar starting in October to do more multi-beam mapping. I wanted to talk very briefly about the Center for Ocean Mapping and Innovative Technologies. This is a grant proposal that's pending. We put together a proposal back in June. It's for a 5-year, $9 million cooperative agreement between Noaa and CMS. It involves 8 of the faculty and another 6 of the staff. The goals of this are to establish and conduct an innovative program of research, to develop an education program, which includes educating existing working staff for Noaa and other people, as well as a public education mode, and then to expand and augment Noaa's capacities to particularly to respond to coastal disasters. So it's a really big project, which, if we are fortunate enough to get it, I think it would be a really great backbone from which we can develop other projects. One of the real attributes, I think, of our proposal is the notion of these test beds that we have around the Tampa Bay region. This is a large spar buoy that Tim Dixon and his colleagues and Chad and others were able to install near the Egmont Key. And so if you go out there, you see this. This is a 90-foot long spar anchored by a 25,000-pound cement anchor. It gives us a data point of very precise water levels, which is important if you're calibrating mapping instruments. And so this, combined with the ports and comps water sea level water gauges in Tampa Bay, and also the elbow as a test bed, I think is a really important aspect of that. And as well, what we want to do is try to look at other technologies. As I said before, I mean, we spent $1.5 million mapping 2,400 square kilometers. There's got to be more cost-effective ways to do that. And so hopefully we can look at these alternative technologies as well. Very much. Sorry for the little mess up in the points. I'll turn it back to you, Sean, now.
Thank you very much, Steve. And you're on time. Thank you. Yeah, we have a couple minutes for short questions. So if you want to ask a question, please unmute yourself, or you can type your question. I can read. I hear silence.
Well, I'll go ahead and break the ice since I love to ask questions. Steve, just a quick question regarding the expected response from Noaa regarding the mapping center. Do you have any idea of when they're going to be making decisions?
I don't. I know that in the RFP they said that they would be evaluating him in July. So I expect, sometime relatively quickly we're going to hear one way or the other on this. So keep our fingers crossed.
Okay.
I have a quick question, if it's okay. I was wondering, when it comes to calculating the abundance of fish on, say, sand versus the rocky reefs, did you guys make any kind of modification for how close the sand was to a rocky reef? Because I would assume that there's probably more fish on sand that is closer to a reef than that is further from a reef. And so those densities wouldn't necessarily be equal.
Yeah, that's a really good point. These are not binary choices. And a lot of times in ecology, you see the highest abundance and the highest population density at the edges of transition zones between one habitat and the other. This is one way to do this, to classify them into binary or absolute bins. Alex has done a lot of work on, for example, if there are transition habitats and others, and so this is sort of the lowest common denominator aspect of that. But there are multiple habitats there. This was sort of a first cut, but you're absolutely right that there are nuances to the classification schemes.
Thank you.
Well, thank you, Steve, and thank you very much. Let's move on to our next speaker, Dr. Tim Conway. So Steve covered an excellent overview on the benthic mapping and population mapping, and Tim will talk about water column chemistry on West Florida Shelf and Gulf Stream. So we move from benthic to water column. Tim, it's all yours.
Can I share my screen, or does it? Yeah, okay. Does that work?
Yes.
Okay, thanks. So yeah, I'm going to address the rather ambitious title, which was Disentangling Ion Cycling on the West Florida Shelf and in the Gulf Stream. But really, I want to just introduce you to some of the work we've been doing on micronutrients in the region. And this is work that's involved a lot of people. So I wanted to highlight my collaborators on this project, especially Brent Summers and Travis Mellett in mine and Kristen Buck's lab at CMS, who just graduated, who measured a lot of the data here. Also Salvo in Kristen's lab, and then Drew Chappell, Matt Charette, and Angela Knapp, who are very involved with these cruises. Okay, so when I like to talk about the Gulf Stream, I like to start with this picture, this map from 1786 by Ben Franklin, really just because it makes the point about how important the Gulf Stream has been historically and how sort of present it is in the public consciousness. So the Gulf Stream is this very fast-flowing, important current in the North Atlantic. You can see here sort of 30 sphere drops through the Florida Straits up to about 150 up through Newfoundland. So this current is really important for circulation and then for transport and navigation through history. But we tend to think more scientifically, so thinking about the Gulf Stream in sort of more scientific sense, it's also incredibly important for heat and salt transport in the Northern Hemisphere. So you can see here sort of a nice animation from NASA showing how the current moves all the way through the North Atlantic, influencing the whole of North Atlantic gyre. So it's very important for moving heat and salt from the low latitudes to the high latitudes. And this again is something that's really very present in the public consciousness, as this really rather extreme example indicates. So this is obviously the film The Day After Tomorrow, but it does make the point about how the Gulf Stream can influence Northern Hemisphere climates. So it's something that the public is very aware of. But we work on biogeochemistry, and this is something where the sort of Gulf Stream system is really very understudied. We don't know very much about the biogeochemistry of the system, especially for trace metals. If we think about the North Atlantic and the Gulf Stream in terms of biogeochemistry, so for example, the nutrient nitrate, and this is a cross-section through the North Atlantic from North America in the west down to the Gyre in the east, we can see the Gulf Stream very clearly as this very sharp physical and biogeochemical front. So it divides the slope C on the margin, which is high in nutrients, from the very nutrient-poor oligotrophic Gyre waters. In recent years, back sort of 2005, more attention has been placed on the role of this system in nutrients in the North Atlantic. This paper by Jamie Poulter back in 2005 really set the scene for understanding how circulation of the North Atlantic controls nutrient cycling right through the Gyre in subtropical mode water. More recently, some more work by Jamie Poulter and some work by us looking at how eddies crossing the Gulf Stream can transport those nutrients from the slope sea into the North Atlantic Gyre. So there's a lot of interesting things going on. This is a very dynamic region with the potential for a lot of interest. The other thing about the Gulf Stream system, and this is sort of what I'm going to talk about today, is that the Gulf Stream provides this really important link between the warm and salty Gulf of Mexico Caribbean system and the North Atlantic Gyre. So there's a lot of potential for transport of nutrients, and that's something that's very understudied. So if we sort of zoom out and look at a very simple schematic of the circulation of the Gulf of Mexico and the Caribbean, we can see here the Gulf Stream sort of leaves the system. We can also think of North Atlantic water entering the system into the Caribbean. And so we can think of this simply as the simplest as water going in and sort of coming out. Obviously, it's more complicated than this. We also have to think about a range of internal currents and other circulation. But this is the sort of framework we're thinking about. And so where I get interested in this is what happens within the system. So we can think of water entering from the North Atlantic, passing through the Gulf of Mexico and being modified by various processes before it leaves back into the North Atlantic. So specifically, we're interested in what nutrients are added by shelf sources in terms of submarine groundwater discharge, river sources like the Mississippi, atmospheric dust, and then what happens in the Gulf of Mexico in terms of cycling. Is it a nutrient's being taken up? How are they being modified? And so we can sort of sum this up with what happens in the Gulf of Mexico doesn't stay in the Gulf of Mexico. And that's also very true for people looking at things like the Deepwater Horizon incident, or Steve and I and others have been looking at the importance of produced water radium for potentially being exported from the Gulf. So there's a lot of interest in understanding what's going on here and then what's being exported. The Gulf of Mexico is also a really helpful natural laboratory for looking at oligotrophic shelf areas. So that's why we're sort of motivated to try and sort of tease apart some of the processes that are going on here. So just to give you a little bit of background to the sort of environment we're seeing on the West Florida shelf, these are some nice figures from Travis Mellett's PhD thesis. He recently graduated in Kristen Buck's lab, and from his paper that's just been accepted, I think, in marine chemistry. And I just wanted to highlight a couple of things. So here you can see a transect from their Weatherbird cruise in June 2015. And if we look at the bottom plot over here, where we're seeing that nitrate, silicate, and phosphate, there's a couple of things you can see that really make the point about this system. So first of all, if we look out at the West Florida shelf, we see very low nutrients, low nitrate, low silicate, low phosphate. And that's pretty typical of these oligotrophic shelf waters, sort of nutrient limited. The other thing we can see in the major nutrients is there is some margin inputs of silicate, phosphate. And so that's the sort of framework we're going to be thinking about for metal supply, this potential margin supply and then the oligotrophic shelf waters. So for my portion of this research, I put together a few basic questions just for this talk, just to sort of guide you with the sort of things I'm interested in. And so the first is, from what I've been saying, how do macro and micronutrients reach the oligotrophic West Florida shelf? So what's coming in the incoming waters? what's being added by atmospheric dust or margin inputs. Secondly, what's going on in terms of internal cycling on the shelf by biological activity? So for example, nitrogen fixation. We know there's a lot of diazotroph trichodesmium out there. Phytoplankton growth, recycling. How are they modifying nutrients? Are they taking them up? Are they modifying the isotope ratios? And then, what is exported back to the North Atlantic? Is the loop current affected by these processes? So that's the sort of framework I'm going to talk about today. I should say this is pretty early stage in this research, but I think we already have some exciting sort of preliminary data. Okay, so zooming back out to the whole North Atlantic, just to give you a context of how much metal data exists in this region. This is the one of the most recent GeoTraces products, showing you where we have iron concentration data for the North Atlantic and South Atlantic. By some standards, it's pretty sparse. By trace metal standards, it's incredibly well covered. But what you can see if you look closely, in the region we're thinking of, there's next to no data. There's one GeoTraces section that goes through near Woods Hole, but there's nothing along the shelf. And there's practically nothing in the southwest Gulf of Mexico. And actually, Travis's paper, which I showed you those figures from, is the first paper to actually produce metal data for the West Florida shelf. So this is a system where we don't know very much at all about what's going on. So today I'm going to show you the results of 2 cruises in this region and talk about some of the preliminary findings. So the first was a 2018 spring cruise on the Hogarth out to the loop current, and this was we're grateful to FIO for funding ship time to Kristen Buck for this cruise, and we were able to get samples and collaborate on this cruise. And then the second is a one-day cruise across the Florida Current in spring 2019. And this was a USF New Researcher project in partnership with the Anjari Foundation, who rent their yacht to scientists. So it's kind of nice to do a cruise on a yacht. Anyway, on both cruises, we deployed Kristen Buck's towfish. And so this is basically a device that sails along just below the sea surface and is able to catch surface seawater without any trace metal contamination. So we can get very clean seawater to measure trace metals. Okay, so let's look at some of the data from the first cruise, which is the one across the Gulf Stream. I just put in this nice sort of animation. You can go to this website, you can look at winds. It's nice for hurricanes, but it also shows Oscar ocean currents. This is just taken from yesterday, but you can see the loop current through here and the Florida current through here. And this is the cruise track we did across between West Palm and the Bahamas. Okay, so what did we see? Here's some temperature, salinity, and chlorophyll across the transect. You can see that the Florida current, or the main thrust of the Gulf Stream here, is sort of picked out slightly in temperature. It's not really picked out in salinity, and then there's maybe some influence of countercurrents over in the east. And as you can imagine, this transect is right across this very fast-flowing current, so you might not expect to see much variability. So if we look at major nutrients and trace metals, we can see a few things. First of all, if we look at nitrate and phosphate, they're basically at detection limit. The same is true for zinc and cadmium. So this is pretty oligotrophic water. There's very little nutrients in terms of nitrate and phosphate. We put through the Florida current, there's not a lot of difference. But if we look at nickel and copper, they're pretty much about 1 and 2 nanomole. That's very typical of North Atlantic waters. So some metals are showing sort of oligotrophic conditions. Some metals reflect the North Atlantic. And then say manganese and silicates are quite high and show slight enrichment within the Florida current. And so this looks very much like a combination of the North Atlantic and the loop current. If we compare the sort of data to Travis's work from the loop current in winter over here, we see very similar metal concentrations. So we're seeing, and that makes a lot of sense, right? If the loop current is moving very fast through here, we might expect to see very similar metal conditions. Okay, so what about iron, which is really what I'm interested in here? Well, if we put the iron section on, it's fairly homogeneous. It's about 0.5 nanomoles per kilogram. If you know about iron, this is quite reasonable for open ocean waters. It's not particularly low. It's not very high. And so we see a reasonable amount of iron leaving the Gulf. And I wanted to know, where is that iron coming from? Where's that iron sourced from? Is it coming from sediments? Is it coming from somewhere else? And this is really where iron isotopes, which is what we do a lot in my lab, come in. So we measure the iron isotopic signature of this iron. And if you don't know much about iron isotopes, and that's expected rather, I'll explain these in a minute. But all you need to really take away from this graph is that we're seeing about plus 0.9 per mil in the iron isotopes. It's very homogeneous. We see a sort of similar concentration and similar isotope ratio. So we can sort of fingerprint this iron as having a specific isotopic ratio. Can we use that to try and figure out where this iron came from? So as I said, if you don't know anything about iron isotopes, there's really just two important things to know. First of all is that the iron isotopic signature is fractionated by various chemical processes in nature. That's especially true by oxidation reactions. So iron 2, iron 3 oxidation can drive big changes. And then this chemistry of a iron sample or its chemical history can impart a distinctive signature on that iron that is then transported, and we can use that isotopic signature to work out where it came from. And so just to make this point, I put together a compilation of what we know about iron sources to the ocean. So here is this is an iron isotopic composition on the bottom. This gray line here represents the composition of the continental crust, which is around 0, so that's quite a nice reference. And this is atmospheric dust, which we know pretty much matches the crust. Not surprising, really, if it's coming from a desert. So what about sediments, which we think might be a signature, might be a source? Well, we have some good constraints on iron in sediments. So this is the iron produced in sediments by respiration of organic carbon by microbes. That produces iron 2+, which is very isotopically light. We also think there's another mechanism in sediments that basically releases iron to the ocean that's not very fractionated. It's about crustal, and that's a non-reductive process. I'm not going into the details of how these work. Just keep in mind these sort of signatures, you know, about somewhere around -2 or 0. If we think back to that graph I showed you, we were seeing about plus 0.9 per mil across the Gulf Stream. So none of these signatures really matches up with that. So we're not really thinking this iron is coming from sediments. The one thing I want to add to this plot is a box called ligand-mediated dust dissolution. And this is a slight modification of the dust signature as it dissolves in the ocean. And just to sort of explain what that means, basically we think as dust falls on the ocean and it dissolves, it's happening with organic molecules and various different speciation. And we think the net result of dust falling on the ocean is iron that's bound to strong organic ligands with a heavy isotope signature. And in the North Atlantic previously, we've sort of constrained this isotope signature as plus 0.7. So that's actually what we think may be going on in driving iron in the Florida current. Really that this heavy iron around 0.9, 0.8 is probably coming from dust dissolution, perhaps in the Gulf of Mexico. So that gave us some information. It also, that gave us some information, sorry. If you're sort of looking carefully at these graphs, you can see maybe I've been a bit naughty in that I've taken off a couple of iron points. And if I put them on, we can see this really striking change in iron isotopes as we get close to Florida. This really big change to about 0.1 per mil here. And so actually what we think we're seeing here is this shift from where iron is dominated by dust to iron being dominated by a sediment source, probably from the margin. And this sort of really typifies how iron isotopes are quite useful, because if you look at the concentrations, there isn't much change in the concentration. And so we wouldn't really be able to tease this apart from concentrations, but we can see it in the iron isotopes. So that's kind of cool, I think. How does that compare to the rest of the North Atlantic? Well, like I said, we don't have a lot of data, but we do have data across the Gulf Stream further north from this geotraces section. And if we put that on, I just picked out 2 water column stations, station 1 in the slope C, station 3 out in the gyre. And you can see here there's some distinctive differences between the stations. Station 1 has more slightly elevated iron, and it has very sort of 0 per mil signatures, this sort of crustal signature. And the one out in the gyre has slightly less iron, but heavier iron isotopes. And actually, if you look at the difference between these 2 stations and the difference between here and here, we get almost exactly the same number. So that was very striking to me. It's a small data set, but you can really see this sort of transition from a sediment-dominated environment to a dust-dominated environment. Okay, so let's move back into the Gulf of Mexico and think about what's actually going on the West Florida Shelf and the loop current that might be sort of creating these signatures. Are we seeing the same thing over there? Do we see a lot of dust? What are the iron isotope signatures there? So I'm going to just put on the data. You have iron concentrations in the top box, iron isotopes in the bottom box, and then this brown bar just represents the sort of average crustal composition, just to give you a kind of a grounding here. And that'll be the same through these plots. So when you look at this, you see there's quite a lot of variability in both iron concentrations and iron isotopes. We can look at this a little bit more systematically, which will help. And that's to divide these regions into the inner shelf, the outer shelf, and the loop current. And this is based on Travis's salinity and other parameters. So we have some constraints on where these boundaries are. And when we do this, we can see quite different regimes for iron and iron isotopes. So I just wanted to highlight a few things. First of all, the shelf iron is really very high. It's about 6 to 10 nanomoles. If you remember, in the Florida current, it's about 0.5. In the open North Atlantic, it can be 0.1 nanomole. So this is really, really enriched in iron, presumably coming from the margin. If we look at the iron isotopes in this region, we also see really quite light isotopes here, about minus 0.4 to about 0.1, 0.2. So it seems that we're seeing an iron source on the margin with a pretty distinctive light iron isotope signature. If we look at the concentrations, we see a big drop in concentrations on the outer shelf. But if we look at the iron isotopes, we can actually see that the signature extends out. So even though we can't necessarily see iron, this high iron extending out, we can see the signature of the margin extending out. So we think we're seeing iron coming from the shelf out into the further out into the ocean or the Gulf of Mexico. So that's pretty interesting. We can think about that a little bit more later. The other obvious thing to highlight is these heavy values. This one here especially is plus 1.25 per mil. I think this is it's either the heaviest or the second heaviest iron isotope data in the literature for seawater. So that's pretty dramatic, pretty striking, and suggests that something really quite interesting is going on out here to drive these values so isotopically heavy. And so what might that be? And this is something that, we're really hypothesizing, but we'd like to do more experiments to think about. The other thing that's out there, on these cruises is a lot of trichodesmium, the nitrogen fixing diazotroph. So this is a nice picture from Angie Knapp, and you can see in this brown these slicks of trichodesmium, these nitrogen fixing organisms that are out there, and they need iron to fix nitrogen. So it's possible that uptake by iron into these diazotrophs could be fractionating the iron that's in the water. So there's a couple of possibilities for that. One is, as with things like carbon, they're just taking up a lot of iron and there's a fractionation. So they're leaving behind a lot of heavy iron. The other possibility is the redox process is going on as they take up iron, which we know to be true, so that could be affecting it. And the second possibility is that it's not trichodesmium, but it's bacteria associated with trichodesmium. So there's this nice cartoon from Basu et al., basically a schematic showing these trichodesmium colonies capturing dust particles, and you see these little blue bacteria that are associated with the colonies. These bacteria produce these siderophores, these little half-moon-shaped organic ligands, and they pick up the iron. And so one possibility that I think is quite likely is that when we have dust dissolution associated with trichodesmium, with these bacterial siderophores, is that we end up with iron bound to siderophores that's really very isotopically heavy, greater than 1 per mil, maybe 2 per mil. And this is, although we don't have any sort of data in situ to prove this, it's something we like to plan experiments with. But it is consistent with experiments in the lab that show that these strong iron binding siderophores pick up very heavy iron, just because it's favorable at equilibrium. And it's also quite consistent with emerging data sets from some other oceanic environments like hydrothermal vents, where we think that siderophores are very important. So that's one possibility. So that's a sort of interesting aside, but it really does capture how interesting the West Florida Shelf is and how sort of exciting to me some of these data are. So I want to come back to these lighter values and see if we can think more about where they're coming from, or how this iron is reaching the West Florida Shelf. So here's a little bit more data from the cruise. This is a nice figure that put together by Angie Knapp. So you can see the two boxes show the outer shelf and the inner shelf. Just to get you sort of grounded, the bottom axis is dissolved organic nitrogen, and then we see barium, silicate, iron, and salinity. And so really just to summarize what we're seeing, in the inner shelf, we're seeing this region that's sort of low salinity or lower salinity, very high iron, high barium, high silicate, high dissolved organic nitrogen. Also very high radium that's not shown from Matt Charette's work. And so what we think is going on here is that this is coming from submarine groundwater discharge onto the shelf. Radium is an especially good tracer for that. And so we think that submarine groundwater sources are adding these nutrients, especially dissolved organic nitrogen, and then these micronutrients like iron. And so this is our working hypothesis for this system. It's something we're proposing to do more cruises to try and understand better. But it's consistent with earlier findings by Matt Charette that suggested that some seasons 100% of nutrient fluxes can be coming from submarine groundwater discharge. So I wanted to say, I wanted to ask the question, do our iron isotope data support this? This iron could be coming from dust, or it could be coming from somewhere else. Is what we have consistent with submarine groundwater discharge? So if we go back to sort of my literature summary of the different sources, I can add submarine groundwater discharge to this figure. And I should say that all this data comes from one study in Massachusetts. It's all from one submarine groundwater study. And you can see there's quite a lot of range in this one study. So we have really very poor constraints on the submarine groundwater discharge end number. And we don't have any data for the West Florida Shelf. Or rather, I should say we actually measured some this week. So this is data that's hot off the press. I got it, I think, yesterday morning. So bear with me if it's not entirely interpreted, but I think it's quite exciting and I wanted to include it. So we looked at submarine groundwater signatures in the aquifer at Sarasota. So this is a figure from Charette et al. 2013, which looked at radium in these groundwater wells. And you can see here these GW points, these groundwater wells. Matt was kind enough to give us samples to look at iron isotopes in these wells. So that might give us some constraints on the submarine groundwater signature. So here's the data, just plotted by longitude simply. And you can see there's quite a bit of scatter from about 0.6 per mil down to minus 0.6 per mil. But it does start to give us some constraints on what the groundwater or the primary groundwater signature might be for iron. We can actually look at this a bit more systematically. So this point up here that's pretty heavy is coming from a shallow aquifer that's very low in iron. These are coming from the superficial aquifer that's quite high in iron. And then this one over here is a very high salinity point. So we can perhaps focus on these right now for thinking about the groundwater signature, at least in the superficial aquifer. We can also look at that a little bit, or rather, I looked at these data in the context of other parameters. The most obvious thing that stood out to me was that there does seem to be some patterns with salinity. We can sort of put a very preliminary look at that. And you can see that perhaps at these very low salinities, we're seeing lighter iron isotopes. And at these higher salinities, we're seeing more crustalline isotopes. So as I said, this is very early data, so it's not really possible yet to say whether these correspond to two different iron sources or whether this is some fractionation process that happens with salinity. That's certainly possible, but it does show this some things going on that we can start to look at. So this is pretty exciting to me. But what it does do is give us a sort of an overall sort of range of submarine groundwater values that we might expect on the West Florida shelf, perhaps between about -7 and +0.2. And actually, if we think about what we're seeing in that cruise data, it's actually really quite a similar range. So while this doesn't, definitively prove it's coming from submarine groundwater, it's certainly very plausible that the range we see in the aquifers is very similar to the range we see on the shelf. So that was quite nice to see. The second nice set of data we got this week was looking at some of the blue holes. And this is not Florida, but it's one of the most famous blue holes. And these are sinkholes that have sunk. Yeah, this is a great blue hole in Belize, but we also have these on the West Florida shelf. So Moat Marine Lab and Florida Atlantic have been studying these blue holes recently. This is the Amberjack blue hole at Sarasota. And these are really very interesting environments. This is a nice schematic from their work looking at the Amberjack blue hole. So you can see you have the sort of overlying seawater, you have this sinkhole, and if you look at the sinkhole, you can see these different oxygen horizons. So oxygen is very variable in these, or changes systematically, but it's very variable in these sinkholes. So you have this sort of oxygenated surface, and then you have this very anoxic deep water. And this is very close to the, close to the water, 100 meters down. And if you know anything about iron redox, that iron and oxygen, whenever there's big oxygen changes, you see big changes in iron speciation, iron redox chemistry, also iron isotopes. And so they were nice enough to provide us with some samples, which I also just got the data yesterday. But here's the iron concentrations and the iron isotopes for this blue hole. And the first thing I want to draw your attention to is this is in micromoles per kilogram. So this is 1,000 times the nanomoles. So it's really very high iron. And if we go down to this anoxic region in the bottom of the blue hole, we see these really high iron concentrations, about sort of 300 micromoles per kilogram. So there's a lot of dissolved iron in these systems. If we look at the iron isotopes, we see a transition from sort of higher in the blue hole into this anoxic zone. It's very isotopically light. And that's really consistent with this idea of there being a lot of iron 2+, a lot of light iron produced in anoxic conditions. So again, we have this potential end member to the West Florida shelf that's pretty similar to the groundwater end member. And of course, the question here is, does any of this iron make it out of the blue holes? And what is its isotope signature when it does? You can see if you look at the water column higher up in the blue hole. And this data, the error bars are a little bit big, so we need to redo this, but you can see that it's isotopically heavy. So there's some interesting questions here about, is iron fractionated as it leaves? Is this a different source? And ultimately, does this form a source to the overlying waters? So pretty new data, but I think it's pretty exciting to see what's going on. So this is something we're very much still working on. We're proposing to do more cruises, to do a more systematic approach with multiple parameters. But for the purpose of this talk, I can put together a sort of schematic of what we think is going on. So just to sort of look at the local sources here, I've put on submarine groundwater. I put on this blue hole as an example. I put on dust. We think these are the major sources of iron to the West Florida shelf. Perhaps we think that once the dust falls on the ocean, modification and uptake of the iron related to trichodesmium and bacteria is producing quite heavy iron. We can then think of the West Florida shelf system as basically, inshore is dominated by submarine groundwater, offshore is dominated by this dust trichodesmium system. The degree to which submarine groundwater supplies the trichodesmium is something that's of an interesting question. And then basically we're exporting in the Florida current something that's about 0.9 per mil, matching this sort of offshore signature. So I think we're starting to sort of see really interesting stuff going on in this system. It's really very much a work in progress, but I think it's quite exciting. So just to sort of conclude, we do think there's a large submarine groundwater source of iron and DON on the West Florida shelf. This is actually really interesting because it's a shelf environment where we can really study this process. This dissolved organic nitrogen source, especially with the iron, maybe influencing both nitrogen fixation and potentially red tides. What I'm excited about this new data is that actually we can see in the submarine groundwater a very similar ion isotope signature to the shelf. So maybe it is a trace of the submarine groundwater. We need to do more sort of high resolution study near this where we know the resources to try and understand that. The other interesting thing we see out in the open ocean or open Gulf is that we see this really interesting process going on driving iron very isotopically heavy. So that's something it's kind of exciting to us because often in the ocean you can't see uptake fractionation of iron just because there's so much chemistry going on. So this might be a really nice study area to try and understand this. And then lastly, just thinking about what happens in the Gulf influences the loop current, ultimately influences the North Atlantic. So I just want to finish with the sort of message that we always need to consider the integrated system biogeochemistry when we're thinking about these systems. Okay.
Thank you, Tim.
I was going to say, do you want to ask, is there time for questions?
Yes.
Maybe we can have a student question first, if there are any.
Oh, yes. Thank you for reminding. We really like to have a student raising questions.
If there are any.
We have 3 people with their hands up, Amelia, Brianna, Michaud, and Boris. So I'm not sure who wants to ask first, but you just unmute yourself and ask.
Yeah, so unmute yourself, go ahead.
Somebody?
Okay, I'll go first. Hi. So when it comes, you may have kind of answered this at the end, but when it comes to the potentially kind of heavily fractionated heavy iron, potentially being fractionated by the cyanobacteria, have you compared that at all to what you see like from the other cruises going across the middle of Atlantic gyres, where you potentially also have a higher proportion of kind of cyanobacteria production going on? Or you were kind of saying at the end it might be overwhelmed by other chemical processes in those areas, or?
Yeah, I mean, the North Atlantic is very heavy. It's like 0.8 per mil, so it could well be this process is going on. But yeah, as you said, really the problem is in the ocean. There's so many processes controlling iron that once you get into the North Atlantic, it becomes quite tricky. This system is really nice because it's simpler. We do see, actually, if you go to the Southern Ocean where iron is very limited and there's very little iron available, we do see similar kind of fractionations in surface waters. And we're not really sure yet if that's again ligand picking up the iron because it's so scarce, or if it's uptake into phytoplankton. It's something it's really interesting, but it's really unknown. Like there's no culture data at all. Iron is just tricky because going from iron in the ocean to iron in the organism, there's a lot of different pathways. It can pick up different species, so there's a lot of potential for different fractionations.
Thank you.
Who's next?
Amelia or Boris?
Tim, I'll ask the question. Hi, this is Amelia. So great data. I think this is the first time that I've really seen that your data and interpretations really show the power of coupling dissolved iron and dissolved iron isotopes into the water column to understand all of these processes that we're trying to see in the ocean. Both are really challenging to measure. I'm not very good at it. So how much data like this is out there in the oceans, and how much is really coming from your work?
There's very little data out there, and actually we're producing a lot of it that's coming out. There's about 3 or 4 labs doing this. But yeah, we're producing a large amount of data now at USF, which is really nice. So we're working in the North Pacific, the Southern Ocean, the North Atlantic, the South Atlantic. Also, there's some nice data coming out, I guess, from Michael Elwood, who tends to do sort of process studies in the Southern Ocean. So it's still really a parameter that's really only studied by a couple of labs.
Awesome, thank you.
One thing I can just say is that we actually have data from another cruise that I put in at the end, just to sort of, in case anyone asked about this sort of thing. You know, one question we're often asked with these data sets is, you know, you went out once and measured them, how representative are they? So actually, we do have another cruise from 2019, so I wanted to include this data as well. And really just to make the point that it is pretty representative of the system, but there is variability. So, you know, time series are important, going back. Regular measurements are important. And actually, Kristen and I, well, Kristen is funded, but we're collaborating on a project at Bermuda where we're looking at a time series of what iron is doing in the ocean.
We have time for one last question.
Okay, so I think now it's my turn. Tim, it was a very interesting study, and I learned a lot about chemistry, which I didn't know before. But one thing I noticed that when you talk about exchange, you only talk about advection by currents. Currents coming from here, coming going there. But there's also diffusion and turbulent diffusion, and maybe as important as advection by currents. And you didn't say anything about it. How are you going to estimate it and what it's going to do? And diffusion also is different in horizontal and vertical, and may have a lot to do with what you see. And if you don't account for the dynamics in the diffusion, then a big part of the physics is missing.
Yeah, I mean, I deliberately go for a very simplified physical approach in this, and I think in this area, I mean, this is a pretty early stage in this data. I'm just showing some initial findings, but I think if we want to understand, you know, this in more detail with more parameters, we need to include some of the physical modeling and think about the different processes going on here, because yeah, that's often a failing of chemical oceanographers, even on these large programs, is that we don't really do a lot of physics. So,
okay. All right.
Thank you.
Thank you, team. We are a little behind schedule, so I have to cut the questions. I'm pretty sure you have questions. I do, but let's reach out to team afterwards. So we need to move on. So let's have a short break. Let's come back at 10:55. So we have a 8-minute break. So be here on time. So this is your time for coffee, tea, and a bio break. And see you in a few minutes. Thank you. Okay. I think we are almost on time. So it's 10:56 now. We should start our second half of the morning session. So the previous two talks cover basically the Gulf of Mexico and Gulf Stream. But I want you to know they also work on other areas of the ocean. Okay? Like a team has been working on the Atlantic. After all, we are not a College of Gulf of Mexico Science. We are College of Marine Science. So the next two talks, you'll see how far we work from our backyard. And our first speaker, Dr. Don Chambers, will talk about Southern Ocean fronts, followed by our second speaker talking about marine chemistry in that same ocean. Don, please take it away. Thank you.
All right, thanks, Wangmin. Let me share my screen. And let me know if we're having an issue with the double screen or anything. All right, I think this is working.
Looks good.
Good, hide that. Hide that. All right, yeah, so I'm going to talk about the Southern Ocean front, some work that I've been doing on it, some work that I'm continuing to do on it, and also present some results that other people have as well. And I hope by the end of this talk that you have a better understanding that fronts are a lot more complicated than kind of this cartoon picture that a lot of people have of the front. So these are an estimate of the positions of the main fronts that we consider for the Antarctic circumpolar current. Essentially the fronts that pass through the Drake Passage and exist in all ocean basins around Antarctica. And that's the subantarctic front, the polar front, and then the southern ACC front. I won't be talking too much about this one because it doesn't transport a whole lot of water. As you can see, most of the water that is transported through the Drake Passage comes from the subantarctic front and the polar front. And so when most people think of the fronts and the Southern Ocean, even scientists who are studying the ocean there, this is the picture that they have. A more or less static front that meanders a little bit, but is generally moving eastward to southeastward and carrying water and water properties around the Antarctic continent. This is a picture from a study that I did a couple of years ago where I was comparing different estimations of fronts. It's a little bit busy. But the red colored lines are different estimates of the subantarctic front. The blue lines are different estimates of the polar front using different methodologies. The cyan are the southern ACC front by different methodologies. And then these orange dots are estimates of frontal positions, and I didn't classify them as either subantarctic front or polar front. I just classified them as there is some sort of frontal motion here, and that's based on kinetic energy, based on surface geostrophic currents. And the key point here is that in some areas, these different estimates agree quite well. In some areas, they disagree very wildly. So for example, right here, south of New Zealand, one estimate of the subantarctic front has it shooting very far to the north. Another one has it shooting very far to the south. My estimate kind of has it in between. And these aren't necessarily because of different time spans of these estimates. The ORC estimates are based on basically every hydrographic section they could get their hands on up to 1995, which are pretty limited. The Kim and ORC is based on looking at contours of dynamic topography from a satellite product. And my data are based on the kinetic energy from similar altimetry data, but processed in a slightly different way and over approximately the same time period. And you can see that we disagree wildly on what's going on. And in the course of this talk, I'm going to explain why some of these differences arise. And it's based on certain assumptions that are made about what is a front and how you can classify a front and how you can use various data products to determine the frontal position. I like showing this because this takes us away from the cartoon representation of what a front is and starts to give us an idea about what's really the Southern Ocean looks like in any snapshot in time. So this is from a eddy permitting or eddy resolving high resolution model of the Southern Ocean, a snapshot for 1 6-hour period in that model. And you can see that there's no clear continuous ribbon of circulation moving around a frontal area around the Southern Ocean. It bifurcates, it creates jets, there's eddies. And so these are basically speeds of the surface current in the model. And you can see that there's no continuous motion along a front. So for example, this right here is a jet. It kind of ends here, but it splits and becomes a jet here. And so these are very turbulent region, and trying to determine a frontal position in this turbulent region is very difficult and prone to uncertainty. And I think this is one of the aspects of frontal research that has only recently become appreciated, is that there's a lot of uncertainty associated with the determining the positions of these fronts. And that really has not been communicated very well in the simple cartoonish pictures that most people think of. So this is the point when I would typically ask the audience to raise their hand if they have heard of the idea that the fronts in the Southern Ocean are moving south due to the winds propagating south. Can't do that virtually, I'm sorry, but I suspect that there would be quite a few hands saying, yeah, I've heard that theory, and I've seen evidence to support that. And I want to talk about that a little bit, because this gets a little bit into cognitive bias in science, and I think it's something we all have to be very careful of. So this is the paper that is referenced in 90% of the recent studies that focus on winds shifting south in the Southern Ocean, and based on a poor understanding of how the actual dynamics of the Southern Ocean are, they infer that the front should be shifting south as well. I'll get to that in a second. But in this study, they took climate models and they forced them by winds based on pre-industrial carbon in the atmosphere up to the 1700s. They added carbon dioxide and greenhouse gases into these models. The winds adjusted. They compared them to modern day observed winds and reanalyses. That's what the NCEP, sorry about that, the NCEP and ERA 40 curves are. And then they argued that they're close enough, and so we can use those to predict what's going on into the future. And in the study, those climate models all consistently showed that the winds were shifting south and they were strengthening. There was a small aside in the paper where they acknowledged that the models were slightly biased compared to the observations, but anyone with any knowledge of statistics and quantification of data will see that this is not a slight bias in the bottom picture at position. That is a pretty substantial bias in the climate model position of the core of the Southern Ocean winds. There's also a fairly significant bias in the strength in the Pacific and also in the Indian Ocean. And so essentially, these models were underestimating the strength of the true position of the winds when they started their prediction run, and they were grossly underestimating the location. The winds were far too far north. It's up to 5 degrees too far north in the Pacific. And this isn't even really acknowledged in the paper. Most people who quote this paper don't even comment on this, but this is a good sign that their model had not been completely spun up in order to match the current observed winds. And so because of that, it's hard to accept that their forecast is correct, because the model is still spinning up, and to spin up to the current positions, winds would have to strengthen and winds would have to shift south. And in fact, the authors of this paper, about 6 or 7 years later, they updated their climate model to make it better match the observed winds, and got a much better match in the position and strength. And lo and behold, their prediction of how much the winds would shift to the south and strengthen were much less than in this original paper. But this is the original paper that's quoted all the time, and that other paper has been mostly ignored by climate scientists. And so that paper led to supposition that if the winds are shifting south, then the fronts should be shifting south. And so people jumped into all kinds of ways to try to see if the fronts were shifting south. And so this was one of the early papers that came up with some supporting evidence for that idea. Essentially what they did is they found a contour of constant dynamic topography that was associated with strong jets in the ocean south of Australia. They identified whether that jet area was related to the polar front or the subantarctic front. And then they took that contour of dynamic topography and assumed that that front would have to stay along that same contour of dynamic topography throughout the entire Southern Ocean. And then they looked at how that contour adjusted over time. And they showed a very nice decrease over time, meaning the latitude was changing and that it was shifting to the south. Now, that is one evidence of the front shifting south, assuming that their supposition that the front would be along this isoline of dynamic topography. And this has actually been really taken by the biological community, especially those studying penguins for some reason in the Indian Ocean that are dependent on the position of the polar front for their foraging. And so they've been doing not the dynamic topography isolines, but they've been using isolines of constant sea surface temperature, and arguing that the isolines of constant sea surface temperature and climate models are shifting south. And so that means that these penguins are going to have to forage farther and farther and farther in order to find food, and that will create problems. The problem is that both of these arguments are completely flawed, because they don't account for the fact that the Southern Ocean is warming and sea level is rising. And this is a very simple cartoon. And a paper came out about 5 years ago by Sarah Gilly from Scripps that, really argued this very strongly and demonstrated it very well. And that actually is kind of ignored by the community. And this is what's going on. Here is the original dynamic topography. So where it has zero distance here, imagine that's just off Antarctica, and then it moves to the north. And this is just a cartoon of what the dynamic topography would look like if you had two frontal positions. There would be a steep gradient where you would have the polar front, then it would kind of relax, and there'd be another steep gradient where you would have the subantarctic front. And if sea level is rising, that whole curve just shifts upwards. Okay. Now, if you look at the isoline for example, the 100 centimeter isoline, that though appears to have shifted south, right? Well, that's because that isoline for the 100 centimeter dynamic topography is really what was 95 centimeters 10 years ago. And it's only due to sea level change or warming. And if you actually compute the gradients of this, convert it into velocity, which is associated with the front, that hasn't changed at all. And so there's been a large group of us in the scientific community that are interested in determining fronts of the Southern Ocean that argue you cannot use this isoline argument of either sea surface temperature or dynamic topography to argue that the fronts are shifting south. You can only use the gradients and see if those specific gradients are shifting south. And so actually a group of us got together and wrote a small rebuttal to the penguin study, and used climate models just like they were using. It wasn't the exact climate model that they were using, but we showed that if you just use the sea surface temperature isoline, you would get a southward shift of the polar front. Whereas if you actually looked at a more accurate measurement of the front displacement based on the density gradients, velocities in the model. In fact, in this one, we used the full surface to depth integrated velocity across the ACC. There was no substantial shift. So the argument of using isolines of either sea surface temperature or dynamic topography is just fundamentally flawed. And so that brings to work that I've been doing for the last 3 or 4 years, and that is using the satellite altimetry record, which goes back to 1973, from which we can compute dynamic topography and variations in dynamic topography. And from that, the geostrophic surface currents or changes in those currents. I've been looking at ways to use that information to better quantify not only the positions of the fronts over time, but also an uncertainty bar on those. And I think the uncertainty bar is actually probably the more important aspect of the research that I'm focused on, because we have to understand that it's very difficult to actually determine the position of this front in the turbulent environment that it exists in. And this is just a schematic of essentially what I can get out of the along track data that repeats in time every 10 days or so. By taking gradients of the sea surface height, I can get the velocity that is perpendicular to that ground track. I cannot get the full velocity vector. I can only get the projection of the velocity vector that's perpendicular to the ground track. However, in the Southern Ocean is kind of interesting because most of the motion throughout the polar front and the subantarctic front tends to be almost perpendicular to the ascending ground tracks of the altimeter. And in the areas where it moves to the northwest, it's almost perpendicular to the descending passes. And so the strongest component of the velocity vector actually tends to be perpendicular to the ground tracks in these areas. So I can actually recover a substantial portion of the full surface velocity using this method. And so my first approach was just to take those velocities and compute a kinetic energy measure. And here I was looking at the variations in kinetic energy. Very simple calculation. I was averaging it over 3-year time periods and then plotting it along each ground track as a function of latitude. And so you can see there's this envelope of enhanced kinetic energy. It's not static. It changes very dramatically. And you can see that there are periods where there's enhanced kinetic energy in areas where a few years later, there's no enhanced kinetic energy. So it varies quite a bit within this envelope. But you can start to see the border of this envelope is a reasonably good measure that there is some sort of uniform density gradient in here, indicating some sort of front exists within this area. And so the algorithm that I put together to study this and assign some uncertainty to it was to essentially find the midpoint of this broader envelope and assume that the front was somewhere around that midpoint, but also include the bounds of the envelope as a type of uncertainty on how we could actually determine where that midpoint was. And when I did that and looked at it where I was able to determine that and look at shifts of that frontal position over time, you know, some people might try to look at this and try to argue that there's significance in some areas, but really these are not statistically significant from no shift in the front at all. And there might be some areas where there might have been a shift, but it's actually more northern than southern. There's a few here in the Indian Ocean where there might be some indication of a southern shift, but overall there's no systematic shift in the front. And you know, I published this a couple of years ago, and I've been continuing work since then. And that's what I want to talk about here in the last part of the talk. And this is really preliminary work. It's just stuff I've been doing over the summer. And one of the big problems with the current methods that I'm using, that other people are using, is that there's a mixture of eddies, velocities from eddies, and velocities from these jets. And eddies can exist anywhere in the Southern Ocean. They're not necessarily created by jets spinning off. They can be formed by local wind stress curl events. They can propagate in from other areas. Jets, however, are resulting from the meanders of the main flow along the front. And thus, jets are more related to the position of the front. Eddies are not necessarily so. And so my goal over the summer was to see if I could create what I call an eddy-free altimeter product that I could actually use to compute the velocities that are predominantly associated to jets and not associated with eddies. And so luckily I have work done by Dudley Chelton for the last 2 decades that I can benefit from. So I don't actually have to detect what is an eddy, what is not an eddy. He's done all this hard work for me, and he actually puts out a database with eddy positions, amplitudes, diameters, things like that. And so all I have to do is match it up with my data and then do kind of a estimation problem to remove that eddy-like signal in the dynamic topography. And so here's just a picture from one track at one day. And I've basically done this for all the data, all the ascending passes since 1993 and up to 2015 to create what I call the eddy-free dynamic topography. And essentially, the red dot or the orange dots are where Chelton's database indicates that there was an eddy signal. And you can see that the eddy causes a Gaussian type of shape in the dynamic topography. And so it's relatively straightforward to take that shape and do a little nonlinear estimation, allowing for the fact that the position of the eddy may be a little bit away from the track, and be able to remove a Gaussian from the data and create this eddy-free dynamic topography. There is some uncertainty associated with this, and I'm in the order of quantifying that. But for the first step, this is dynamic topography that is probably not related to an eddy and is most likely related to one of these jets. So, for example, here, note that there is a Gaussian type of signal here, but there's no eddy in the database that supports that this was caused by an eddy. This is most likely caused by a jet. And so the statistic that I've been looking at in order to identify where these frontal positions are and kind of their breadth is the percent of occurrence of large velocities to the southwest. And so this is just a snapshot for the data from 2000, and this is wrong. It's not 2020, it's 2010, because I only go up to 2015 in this. But you can see that in this area here, I'm around 50 degrees. So this is a pass that goes just south of New Zealand. You know, there's a high percentage of occurrence every year of strong velocities. I also note that the center of that strong occurrence of velocities is significantly north of where Orsi says the subantarctic front is at that latitude. That indicates that his result is likely biased a little bit to the south. Then there's a broad range of area between 52 degrees south and 59 degrees south, where you can have high variability, high percent of jets in some years, low percentage, but then it will shift around. And this is kind of an average area where Orsi identifies the polar front. And so here we have a situation where there's one front that's pretty well defined because it occurs all the time. And here you have another area where the front is not well defined at any particular time because these jets move around quite significantly. And so now I'm at the step of trying to quantify this for every pass. And just a quick look at what this looks like is in this plot showing the percent of time that you have these high velocities. And I've just overlain it with the more recent Orsi frontal positions based on the isolines of dynamic topography. And so if my results agreed with Orsi's, then every time that you see these whites, which are the highest percentage, you would expect his front to be aligned with that. And as you can see, it really isn't in a lot of locations. For example, here, also in this region right here, where the subantarctic front and the polar front come very close together, it's very difficult to isolate them because you have so much jet activity in the region. In fact, and some could argue that the fronts actually merge here and it's almost impossible to differentiate them. The same thing occurs here. And so this is just a snapshot of two different times. This is 2000 and this is 2005. And you know, I haven't quantified this. This is very qualitative yet. I just finished this a couple of weeks ago. But you can see by comparing the high percentage and the locations of the high percentage in 2000 to in 2005 in this area. Here, it appears that the center of where these jets occur is farther north than they were in 2000 and a little bit stronger. And so the goal of my future work then is to, you know, repeat this analysis with descending passes. So all these areas where I don't have data, that's primarily noticed when the front shifts. And so that's when the descending passes will become more important. And then to develop an objective algorithm to identify where the midpoints of these jet activity are, their widths, how strong they are for each year. And so the ultimate goal of this is to come up with a quantified position of the fronts with uncertainties associated with them that we can actually use to see how they're moving in time. So with that, I will stop and answer any questions.
Thank you, Don. We have time for a couple of questions, short questions. Students first. Unmute yourself if you ask a question. No.
No one cares about the Southern Ocean.
I do.
Hi,
I
they-
have.
John.
Or they just believe that I'm 100% correct.
Yeah. Well, I heard you got a new NASA project to work on this, right?
A student got a student fellowship, yeah.
Okay.
But she's actually working on something that's slightly different, but yeah.
Nice.
Don, this is Mark. This is something I always flub up when I teach physical oceanography. So maybe I could get you to do a guest lecture on this topic next time I teach it.
Yeah, well, you know, I'm teaching a readings course on Southern Ocean dynamics right now, and that's one of the things I point out is that you can't understand the Southern Ocean using spare drift dynamics. And that's where a lot of models and these climate models, I meant to mention that, have it wrong, because the only way they can balance the wind forces is through making the viscosity of the ocean essentially molasses. Because they can't use the real force balance, which is through form drag, which is interactions of the deep currents with bathymetry.
Interesting.
Yeah.
Let's see, the last chance. No, I asked this last time. Any more question? Well, if not, we thank Dr. Don Chambers and start the next talk given by Dr. Nancy Williams on the